Well, good morning, everybody. Welcome to the first day of Math 151. So we're going to start with just some basic physics notions. Now, the first day of Calc 2 always scares people because we start with physics. And the main reason we start with physics is not because of what you're going to do in physics, but the ability to understand and manipulate the units involved. So you see, in math, when we draw graphs in math, or we're asked the slope of a line, or even in Calc 1, when we're doing the derivative of something, we tend to do problems that are unitless in general because we're interested in the mathematics of it. We're interested in the correct setup. We're interested in the correct numerical value. But in reality, almost every problem you've ever done probably had units involved. When you're doing a graph in algebra and you're finding the slope of a line, there's no such thing as a slope that is unitless. A slope is always a rate. It's a rate of whatever the numerator is over whatever the denominator is, and those always represent units. It's just that we tend to not worry about the units in a math class. We're worried about the math. But then you get to physics or you get to chemistry where everything has units and you're not always sure what you're supposed to do. So we're going to go over some of the most basic parts of the things that you need to know. Now, if you're in this class, then your next science class is probably going to be Physics 195, but you're a little bit ahead because you're having the math before you have the physics. That's a huge advantage. But when you walk into physics, they really do expect that you know the units and that you actually understand them fairly well. So let's go over a few things because also it's the symbols and the notation that we use. So when we talk about distance, we usually use terms like displacement. Displacement is how far something moves, and we generally use S. You're going, S. Well, think Calc 1, right? You found the length of the curve, the arc length. That was always S of t, okay? So if you're finding something that's a distance, we generally don't use d for distance because we're using d in the derivatives and other things. It can be confusing. So if my displacement is S, and let's say time, we use t, then displacement per time or speed, which we loosely call velocity, is displacement per time. Now I say loosely because next semester you're going to learn something about velocity. Velocity is not a value. Speed is a value. Velocity is actually a vector. We don't do anything related to vectors in this course. That's Calc 3. The first 2 or 3 weeks of Calc 3 is all vector analysis and stuff. And then you learn about things like velocity, acceleration, and such. Yes, they involve derivatives, but they're vectors. They're not scalars. They're not values. Speed is a number, and the units are displacement per time. So feet per second, miles per hour, meters per second, kilometers per hour, things of that nature. So speed is this, and acceleration, which again, technically it's a vector, but in this case, when we're talking about acceleration, we're talking about acceleration in the same direction you're moving. So for example, acceleration due to gravity and things like that. And in that case, it's speed per time, okay? Or S over T, S over T squared, meters per second squared, feet per minute squared, whatever it is. So we know, for example, gravity, acceleration due to gravity in English standard units is about negative 32 feet per second squared. And in metric, it's about 9.8 meters per second squared. These are constants that many of you are aware of because you may have used them in other classes, okay? So these are very basic units. So I have displacement times speed, acceleration, great. Now, what about force? That's the first major one. Force, okay, well, what is force? Force is mass multiplied by acceleration, okay? And we generally use MA. Little m is generally mass, little a is generally acceleration. Now, what is mass? Okay, well, if you look up mass in the dictionary, it's kind of funny. I've seen different definitions. My favorite is how much stuff is in something. That's what mass is. It's kind of like stuff. There's not any particular thing. So your mass is how much stuff you are made of, and your mass weighs something. But your mass will weigh something different in every environment. In other words, if your mass weighs 180 pounds, my mass roughly weighs 180 pounds on planet Earth. My mass is only going to weigh about 30 pounds on the moon. But I'm going to weigh a heck of a lot more if I'm on Jupiter. Your mass is how much you are. Your weight is determined by gravity and the mass. So mass and weight are not equal. In fact, your mass and weight are as comparable as your height and your weight, or your age and your weight. And a lot of people will say, I weigh this many kilograms, which I always laugh because all the people who are born in an environment other than the United States, they say, well, metric, we use metric for everything. I've never heard a human being in their entire life give me a correct metric weight. Does anybody know what the unit of weight in metric is? I'm just curious. Anybody know?
Isn't it stone?
No, actually, that's an English standard one. That's like the guys in the world's strongest men. It's newtons. That's the only weight unit there is in metric. And none of you use newtons to describe your weight, which I think is kind of funny. So if you're using kilograms to describe your weight, you might as well just use your height to describe your weight. They're completely different units. Kilograms is mass. Kilograms is not acceleration times mass. It's not even similar. So your mass in metric, we generally use kilograms, and I want you to get used to that. In English standard, that's a fun one. Does anybody know what the mass we use in English standard? You know, where we use feet and pounds and miles, that's English standard units. Does anybody know what the mass unit is? It's awesome.
Grams?
No, that's metric.
Pounds?
That's weight. That would be force. Slugs. Yeah, the unit of mass in English standard is slugs. And
Leave it to Americans.
Yeah, we Americans, well, actually, it comes from the Brits. So, you know, yeah, I don't think any of you have ever used slugs as a unit when you're talking about something, but that actually is the American or English standard version. No, we tend to concentrate on the force more than the others. So the units of force that we use generally are going to be pounds or newtons, and we use capital N for newtons. You're generally not going to use other things. Yeah, tons, that's 2,000 pounds. That's not a unit necessarily that we use. And newtons, you know, it can be very impractical because if there's a lot of them, you might say there's a billion newtons. That's okay. That is the unit of force, and we're going to use this, and we're going to get used to it. So force, that's mass times acceleration. The easiest way of thinking of force, most people, they think of weight. Weight is the force due to gravity. So how much I weigh is my force on the scale due to gravity. If you're lifting weights, the amount of weight you're moving, right, it weighs a certain amount due to gravity. So if you're moving the weight, then you must apply a force that's at least equal to the weight you're moving. Okay, so weight is force. They are exactly the same thing. Now, what if I want to move something and I want to measure the movement in addition? Now, this is what is called work. Work, the simplest version of work, it's force multiplied by displacement. Okay, so it would be, you know, your pounds multiplied by your feet that you moved it. So I like to use the analogy, I've got a refrigerator and I want to move it across the room. Now, let's suppose my refrigerator weighs, 400 pounds and it's on wheels, and I want to move it 50 feet. So if I said, how much work do I do in moving the 400-pound refrigerator 50 feet? That would be exactly 20,000 pound-feet or foot-pounds. It doesn't matter what order you say them, but that's actually the English standard unit of work, pound-feet or foot-pounds. That doesn't seem like a practical unit, but if you're using pounds and feet, then that would be the unit you'd use. So technically, again, these involve vectors, but we're not going to worry about the vector part in this course. That's next semester. So the idea in this course is I'm always applying my force in the same way that I'm moving something, okay? So for those of you who remember something like this, it's called a dot product. Don't worry about that. That's next semester. If you're in my Calc 3, we'll discuss that. But so work is the product of these guys, and it is a scalar value. It is not a vector. It's not even like a vector. I don't even want
I have a quick question.
Yes.
If seconds is a lowercase s, is displacement a capital S?
If you were saying seconds, that's a great question. Usually when people are saying seconds, they'll put SEC.
Okay.
Like feet, nobody uses F, they say FT. So if you wanted foot per second, you'd probably say FT over SEC. And that's a great question because the last thing we want is ambiguity. Because in this case, S is a variable, it's not the unit I'm using. Okay, so I like that question. So in other words, I'm using LB or LBs for pounds. Now, this is what work is. Now, what if we're doing metric? Because we're going to probably do more with metric only because I want to prepare you more for physics. So with metric, the units are usually going to be newtons, and this is going to be meters. And we'll use a little, by the way, from a unit standpoint. Okay, we will use little m for meters generally, because again, it's a unit. There's no ambiguity as to what in this case it means. But you never say a Newton meter. Does anybody know what a Newton times a meter produces, the actual unit we use? Anybody say it?
Joule.
Which we just use a capital J. So joules is the unit of work we use in metric. Now, it turns out, what if I'm using, bazillions of these guys? Do I use a different unit? No, you just say, I have 1,000 joules or 1,000,000 joules. But the flip side is, what if I'm using really tiny quantities? What if I use very little, tiny bit of force in very tiny distance? There's actually another unit you would use, and I'm not worried about it, okay? It's 10 to the 5th dynes, D-Y-N-E-S. Don't worry about that. You do that in a physics class. We're not going to get into the micromanaging of, what happens when you use a microscopic version and you use a different word. That's confusing. So we'll just stick with joules because we're just learning the how-to right now. So work is force times displacement, and in metric, we generally would use joules. Now, energy, which is extremely important. Now, there's a few different types of energy. And again, this is not a physics lecture. This is so we can get the units right. But you're going to hit a punching bag. You're going to be punching the bag over and over again. You're depositing energy through your motion. Now, my oldest son just graduated from college with a degree in kinesiology. He's preparing to go to physical therapy and all that kind of school. Kinesiology is the study of movement of the human body and things like that. Okay, what kind of energy when I'm hitting the bag is that called? If it's energy from my movement and motion, does anybody know?
Kinetic energy.
Kinetic, yeah, that's from kinesiology. Kinetic energy is me punching that bag over and over again. The water is moving through the river and you have a dam, and the water, because of the dam, is now turning the turbines and spinning it, and we're generating electricity. The water motion is the kinetic energy. The electricity we're generating because of the motion. It's like, what is the bag absorbing? That's called the potential energy. And the potential energy has to equal the kinetic energy because one of Newton's laws says that energy can neither be lost nor created in this case. In other words, everything has to be accounted for. Now, don't worry about those two things, but you run across these terms, you'll hear, well, what's the potential energy? What's the kinetic energy? Well, numerically, they would be the same. One of Newton's laws that most of you have probably heard, and it's funny because it's not the way Newton said it, because it doesn't even make sense grammatically, but he says for every action, does anybody know the rest?
Equal and opposite and equal reaction.
There's an equal and opposite reaction. Now, the problem with that statement is we're talking about numbers. And so what he means is there's a value that's equal, but the opposite sign because it's directional. And that's what it really means. So what is an opposite reaction? And a reaction that has the opposite sign in terms of direction. Remember, I said it's force times displacement, but technically in the vector sense, work can be a negative value. Now that totally is weird. And I'm going to give you the reason why work can be negative. I'm pushing the refrigerator across the room and I moved it a certain amount. I did a positive amount of work. Let's suppose I want to push the refrigerator across the room, but across the room, is a steep hill and all I end up doing is going completely sideways. How much work did I get done across the room? The answer is actually 0 because my displacement across the room is 0. I want to push the refrigerator across the room. And so as I start pushing, it starts rolling backwards and I stop. How much work did I get done pushing it across the room? I got a negative amount of work done. Negative, why? Because my motion was in the opposite direction to where I wanted to go. Another way of thinking about that is I now need to do a positive amount of work just to get it back to the starting point. So work can be a negative number if the force is in the opposite direction from where you were actually intending to go. That's why the potential and the kinetic energy, the forces are kind of in the opposite direction. When you hit the bag, it's kind of like the bag is also hitting you back. If you decide you're going to punch the wall, it doesn't feel good on your hand. It's like the wall punched you back in that sense. So direction does matter. Now, what energy is, and we use those terms, most people know how to calculate energy, right? Most people know there's a formula for calculating energy, and it has to do with mass and velocity and things like that. Most people know there's a formula. Energy is usually some version of mv squared. Now, it turns out kinetic energy is 1/2 mv squared, but I'm not worried about that. It's the product of mass and the square of velocity, or the square of the speed. So what is this? Well, let's go back and look at this for a moment. If it's mass times the square of velocity, then it's mass, I'll write it out in words, times displacement over time squared, which is mass times displacement squared over time squared. Okay. Now, how does that help me? Well, what if I did mass times displacement over time squared, and I multiplied that by displacement? Would that be the same thing mathematically? But this is mass times acceleration times displacement. But that's force times displacement, and that's the definition of work. So we either have a problem here or we have a really cool identity. Energy is exactly the same as work. There's no difference. And a lot of people think they're completely different animals. No, it's a context thing. I'm working out in the garage. How much work did I do lifting the weights? That's how much force did I apply multiplied by the distance. But it's the same exact answer as how much energy did I put out in lifting the weights. The amount of energy I put out is equal to the work, not numerically, but in every way. It's the same units. So we still use the same units, but it's the context thing. When you turn on the light, how much energy are you using? You're not thinking of how much work you're doing. You're thinking of how much energy am I using? So energy and work are exactly the same thing. And we generally will use metric most of the time, so it's joules. So there is one other piece of the puzzle from a physics standpoint, and it's my personal favorite. It's the concept of power. Now, power is one of the most important things that we study in everyday life and in physics, but a lot of people don't understand how this is related. So you get your electric bill, and you're looking at the output, and you're saying, what, it'll say things like kilowatt hours. Like, what does that even mean? Well, the kilo just means 1,000. That's not a big deal. Power is generally thought of as energy or work per time. It's not just your energy, but it's how fast are you producing energy. So if I'm producing a certain amount of energy over a long period of time, or I'm producing a certain amount of energy over a really short period of time, the larger that quotient is, the greater the power is. So if I do a certain amount of energy over a really long period of time and somebody else does it over a really short period of time, their power number is way bigger than mine. The energies might be the same. So I like to think of it this way. I'm a big football fan. So I'm a big lineman in football, and I'm going to move out you, and I'm going to block you, but I'm moving really slowly. There might be a lot of force, but there's not going to be very much power because I'm not moving very fast. So if I move really fast, now there's a tremendous amount of power. So the units, the English standard units for power are watts. When you hear watts all the time, that's actually a metric. I'm sorry, I said English standard. Sorry, that's a metric unit. Does anybody know what the English standard unit for power is? Actually, should be pretty easy.
Power?
Can you think of any words that we relate with the word power in them? Think of a car.
Electricity or something?
Horsepower.
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 Horsepower is the English standard unit for power. It's like, that's what horsepower is. So horsepower is how much energy per time your engine's putting out. So the greater the horsepower, the more energy per second your car is putting out. That's why your car can do, cooler things maybe. There's more horsepower. So the English standard version is horsepower. We generally think of watts. So when I look at my electric bill, by the way, your electric bill is absolutely and entirely metric. It's never been English standard. It will say kilowatt hours. Well, what does that mean? Oh, if energy per time is watts, then energy would be watts multiplied by time. So kilowatt hours are your power times the time. That's how much energy you use, and that's how much energy you're paying for. Okay, so that's kind of a useful way of thinking about your energy bill. So another way of thinking about this, if it's energy per time, it's also work per time. And I like this one. This is my favorite one, because one of my passions is to study I study human motion as it turns in terms of athletic achievement and things. And I've done a lot of research over the years. I wrote a dissertation a number of years ago on what's called explosive power from a human standpoint. So I say, think of the sprinter in the starting blocks. They're not moving yet. And the gun goes off and they take off. Usain Bolt. Your idea is to reach the maximum speed in the shortest interval of time. A basketball player is getting ready to do a jump. He's not moving, and then he jumps up. A running back in football is in a static position and he's taking off. The idea of explosive power is when you start from a static position and you reach the maximum speed in the shortest duration of time. You don't want to take all day. If you're a sprinter, you want to jog for a while and then do that. So how does that apply? Well, in weightlifting, it's the same thing. You don't want to push slowly. You want to push fast. So what is work? What did we say work was before? It was force times displacement. Okay, so if power is work over time, then it's force, but that would be force times displacement per time. But isn't that velocity? So another way of thinking about power, it's force times velocity. So I like to think of it this way: strength multiplied by speed. See, how much force you're applying when you're lifting weights is equivalent to your strength. Strength is how much you can move. How much force you can apply is the definition of strength. So if you said, I'm going to take the strength and multiply it by speed, that's your power. That's why the big, strong guy moving really slowly doesn't have a lot of power, because there's no speed. That fly that's whipping around the room really, really, really fast doesn't have a whole lot of force behind him, so there's not a lot of power. So if you're a hockey fan, you're watching that 230-pound hockey player going full speed and crashing into another guy. Yeah, that probably doesn't feel very good. Or that linebacker in football who's running full speed and crashing into somebody, that's force and velocity. They're both large, right? So that one hurts a lot more. So these are the units. Now we're going to apply them to a couple of simple problems today. So today, the first part of the class is going to be about work. And there's two types of problems that I want to discuss. Neither one of them are complicated. But the idea is we're going to talk about things that involve variable force, which means that the only way to answer a question is through integration. If my force is constant, then work is trivial. You just multiply the force times the displacement and you're done. But if force is variable, then there must be an integral involved. So the first one we're going to talk about is what's called the spring problem. Now, there's two types of spring problems, the one we're going to do and the one you do in my Math 255, my differential equations class. That one's a bit more complicated. We're going to look at a spring problem. Keep it really simple. This spring problem, we're going horizontally. In the DiffyQ class, we hang the spring and then we put something on it so that it oscillates, and that's way more complicated. So I have a spring that's just sitting there at rest. There's a couple of basic assumptions that we have to make in this problem. And they're two very important assumptions. The first assumption is the spring is long enough that when I stretch it or compress it, I'm not going to run out of room. I'm not going to say, I'm going to give you a spring that's 1 foot long. Now I want you to stretch it 3 miles. Well, that wouldn't make any sense. I'd more likely think of the spring as 3 miles long and I want you to stretch it or compress it a foot. That would make more sense. I have a spring and it's just so long that I'm not going to compress it or stretch it beyond what it physically can do because I've run out of space. That's not the other worry. The other thing is that it is uniform. So it's exactly the same forever and ever and ever. I don't have thick spots and skinny spots. I don't have spots where it's overstretched and other spots where it's compressed. It's identical. It's a slinky before your little brother stretched it out all the way and wrecked it like mine did when I was a kid. I haven't forgiven him for that yet. Anyway, it's a slinky that's perfectly uniform. So if we make those two simple assumptions that it's uniform and it's long enough that I don't run out of room, now we're going to apply something called Hooke's law. And this is so simple. Hooke's law says that the force is going to be a constant times the displacement. So the more I pull, the more force I have. But it'll be a constant multiple of displacement, meaning force equals a constant times displacement. Boy, that makes things really, really simple. That means ultimately when I'm integrating a simple linear function. So if that's the case, then you have to be given certain information. Every single spring, every coil, everything of this nature that exists has what's called a spring constant associated with the thing. The spring constant isn't something automatically you actually have to calculate it. If you've ever looked under a car, there are springs under a car, coils, that might take thousands of pounds of force to get it to move a little bit. Whereas a slinky, you only have to pull on it a tiny bit, perhaps. So every single spring has a constant associated with it, and that constant must be calculated. So you'll always start with something like, when I stretched it out this far, here's how much force I had to apply. Now I calculate my spring constant based on that. Now, once I know my spring constant, now you can say, now if I stretch it from here to here, or I compress it from here to here, how much work do I have to do? Since work equals force times displacement, remember, but the force is not constant, then the work will always equal the integral of force. Now let's call the displacement, let's use x for our variable because we're moving horizontally. Then it will always be f dx, because then the units after integrating would be force times displacement. I'm integrating with respect to small increments of displacement. You're going to start and end at a specific given amount. This is not something you have to guess at. You have to be told this information. And the units you give are based on what the problem is given. So when we do these problems, we almost always go metric. It makes the units just so much easier. So Hooke's law says force is a constant times displacement, but this is not constant. So if we use this variable, then force, I'm sorry, I left out the x. Then this equals kx. So that's what's going to actually go here in the statement. So let's do a very simple example. So let's say it requires, I don't know, let's say 100 newtons of force to stretch a spring 50 centimeters beyond its, and the term we usually use is natural length. What natural length means is the spring is at rest. It's not moving, it's this long. That's its natural position. And now I'm going to stretch it 50 centimeters beyond that, okay? Beyond its natural length. That information will allow me to calculate the spring constant. And now the problem that I'm going to solve is how much work is required to, let's say, compress the spring from how about 20 centimeters to 60 centimeters from its natural length. Again, associate natural length with resting position. Now, the thing you like about this question, it doesn't matter how long the spring is. If I told you exactly how long the spring is, then I've got to give you additional information. I'm just saying the spring's at rest. We're going to stretch it 50 centimeters, and here's how much work, or excuse me, here's how much force I need. Now it's at rest, and I'm gonna start 20 centimeters in, and then you're going to walk up, and then you're going to push it from 20 centimeters in to 60 centimeters in. Okay. How much work do I need to do in that case? So that's what it looks like. So let's start by calculating the spring constant. So since the spring constant, remember we said force equals constant times displacement. The constant, therefore, is the force divided by the displacement. So my spring constant is, where is it? 100 newtons. Might as well circle those. Over 50 centimeters. Now, I'm not going to go a step further because we have a small, just teensy weensy problem. If I said, I want you to measure the area of your floor at your house, and let's say in one direction you decide to measure it in feet, and in a different direction you decide to measure it in meters. Would anybody here say, oh, my floor measures 50 meter feet?
So you need to convert the units.
Yeah, but here's one thing you have to have. You cannot, in any context ever, like in the history of the world or in the future, I looked, you can never have different units for the same measurement. That's not possible. You wouldn't say, and the area is this many inch feet. No, it'd be inches squared or feet squared. Why is there a problem? Because what is a Newton? 1 Newton equals 1 kilogram accelerated at 1 meter per second. So the unit of measure of a Newton is a meter. There is no unit of measure that uses centimeters in this context. Oh, since Newton's already involves meters, I can't have a Newton per centimeter. I've got to convert that to meters. Now, this is not a trick question. This is kind of how things work out. Most people, when they're talking about lengths in metric, if it's small, they'll use centimeters. People don't usually use decimal meters. Oh, I moved 0.15 meters. No, they just say 15 centimeters. It's more convenient. Okay. If something is small in weight in English standard, you might give ounces. You don't give a decimal or a fraction of a pound usually. You know, my steak was 6 ounces. I had 3/8 of a pound of steak today. Well, that would be true, but that'd be really confusing. Nobody speaks like that. So I need to change this to meters. And that's why I'm throwing this problem at you, because this is one of the biggest difficulties we have at first is recognizing the units. So 50 centimeters is how many meters?
0.5 meters.
0.5. By the way, that is not automatic. There's a lot of people that can't remember. The easiest way, what does cent mean? C-E-N-T means what? You may know.
One per 100.
Cent means 100. It's Latin for 100. Oh, so a centimeter in this context would be 100th of a meter, meaning there's 100 centimeters in a meter. That's the easier way to remember. Oh, cent. And when I'm teaching remedial algebra, I go through the prefixes and think of words. You know, what is a century? It's 100 years. What's a centurion? It's my favorite one. That was the Roman commander in charge of 100 soldiers. A lot of people don't realize that's what the word centurion means. Remember, it is Latin. That's what the Romans spoke. So a centimeter is 100th of a meter. So 50 centimeters would be 50 hundredths or 0.5. That is absolutely correct. But I'm not going to use either one of those numbers. I'm going to use 200 newtons per meter. Now I can say this particular spring, the force is 200x. Generally, okay, I already know it's newtons per meters, so x clearly is being measured in meters because force will have to be newtons. I don't need to put the units within here. I find that to be a little bit hard to read. What I tend to do is do the calculation and then put the units on at the end when it makes sense. You can put the units in at every stage, but it becomes kind of hard to read after a while. So now, what is my force in this problem? Excuse me, my work in this problem, sorry. My work is going to be the integral of this, which, by the way, should be absolutely trivial. But what are my limits of integration? Ooh, I'm moving from 20 to 60 centimeters.
Some 0 to 40,
0 to 40. I kind of need those numbers,
20 to 60.
but those are centimeters.
Okay, so 0.2, 0.6.
Yeah, there we go. 0.2 to 0.6. If I go 20 to 60, I'm going to get an astronomically big answer that's not correct, because my limits of integration are distances. So therefore, they still need to be measured in the same units that I used before, which is meters. Remember, my spring at rest, I'm going to move in 20 centimeters, and then I'm going to hand it off to you. And you're going to go from 20 to 60. So the initial 20, we're not calculating that. We're just counting from 20 to 60. So that's why we're using those numbers. 0 to 40 would be if I went from rest to 40 centimeters. That would be, that would be that one. So this calculation should be relatively simple. This would be 100x squared evaluated from 0.2 to 0.6. Oops. Which would be, let me fit it in there, 100 times 0.6 squared minus 0.2 squared. And so let me get out my calculator. So what do we got? 0.6 squared. And I'm sure you could all do this in your head, but why? And so that comes out to be exactly 32 what? What unit?
Joules.
Joules. Perfect. Here's the unfortunate thing. Most everybody in the class is going to get the 32. But a lot of people aren't going to get the units. And unfortunately, the units are just as important as the numerical calculation. And I got some bad news for you. You get to the physics class, you got the 32, but you don't have the joules. I will guarantee you in every physics class in the history of Mesa College, what will you get as an answer? What will you get for credit when you get the joules wrong?
Fail, a 0.
Absolute. That's not even negotiable. My oldest, when she was taking physics at Mesa College, she had never gotten a B in her entire life in anything. She graduated magna cum laude from, college and grad school, but she got her first and only B's in her life in physics at Mesa College. She loved it, by the way. On her very first assignment, it was an assignment where they were doing calculations of stuff, and every problem that they were given was unitless. And so what's the whatever, what's the velocity, what's whatever. And so she did all the calculations. She got every number absolutely correct. And every problem was unitless. And she got a 0 on the assignment because the instructor wanted the students to write the word units after every single number, even though it was a unitless question. I just thought that was mean, but they made a point. Nobody forgot their units on any problem the rest of the semester. And my daughter told me, she goes, most of the class got 0s, but some people got 100%. I go, how did they know? She goes, all the people who got 100% were the people that had failed it the previous semester. So they knew what was coming and they weren't going to share it with anyone. Now, I'm not going to give you a 0 for getting the units wrong, but it is a darn shame when I ask you how tall you are and you say 25 years old. That might be true, but that's not a height. So when you're saying 32 and this isn't a work unit, then it is really an incorrect answer. Joules, because I'm in metric and I'm using newtons and meters. There's no part of a spring problem that should ever trouble you, because the very worst, you're integrating a linear function. That's about as simple as it's going to get in this class. But it's also about getting the units. And for the spring problems, I will generally always stick with the metric because it's just a little bit easier. It's a little bit easier to work with in that case. All right. Now, the next type of work problem is a little more complicated, but probably more common than, you don't do a lot with springs, I'm sure. Now, if you were in the if there's anyone here in the military, you would understand this, particularly in the Navy. All right, you've got a Navy ship, you're out at port, and that ship probably has an anchor so it doesn't, doesn't float away. And if you've ever seen an anchor on a ship, they are huge and they are really, really, really heavy. And before that ship can take off, you've got to bring that anchor up. You're probably not going to do it by hand. So let's say that anchor weighs, at least 1,000 pounds, and you've got to move it at least, let's say 100 feet. Keeps it really simple. I've got a 1,000-pound anchor and I got to move it 100 feet. So clearly that's 1,000 times 100 pound-feet or foot-pounds, 100,000 foot-pounds of work to move that anchor. You all agree with that? And of course, the anchor's being hung with dental floss, because dental floss is really light and I don't have to worry about dental floss. Or is the anchor hung with some really huge, gnarly chain? Probably some huge, gnarly chain that isn't weightless. And as I'm pulling up the anchor, that chain is probably as heavy as the anchor, by the way. As I'm pulling up the anchor, there's less chain as I pull. And by the time I get the anchor to the top, there's no chain left. So in other words, although the anchor, I can say, what's the work done picking up the anchor? That's easy. That's just the weight of the anchor multiplied by the distance it has to travel. But what about the chain? The
That's where
chain
we,
is changing, isn't it? The weight of the chain is changing as I pull it because there's less chain. So in other words, I again have a variable force. So then I'm going to do this problem from a different standpoint. Okay, here's a pulley, and here's a big old heavy weight. I'm going to put WT for weight. It could be a rock. I have a big old heavy weight right there, and I want to pull this up. But the problem is, the cable cannot be weightless. That doesn't make any sense. The cable has weight. So I have to figure out two things. I have to figure out how much work to pull this thing up. Well, that's actually going to be easy. The work to pull this thing up is just how much it weighs by how far it travels. But then I also have the problem of what about the cable? So we're going to split this up. Think about splitting this up into a whole bunch of little pieces. Okay, let's say overall, okay, whatever this distance is, just we can just make up a number if we want. Let's just say it's I don't know, let's say it's 1,000 feet. We'll keep it simple. And let's say this thing here weighs, I don't know, 500 pounds. We'll use English standard in this case. But the cable is not weightless. So let's say that the cable, let's throw out a number. Let's say the cable is 2 pounds per foot. It's heavy. It's metal. It has to be pretty strong if I got to pick up a 500-pound weight. Think of an elevator. I mean, those cables are really heavy duty and heavy. So let's say the cable weighs 2 pounds per feet. I got to move it 1,000 feet. That means the cable weighs 2,000 pounds. So can I just multiply the 2,000 pounds?
no, because it's not all the time it's going to weigh that much.
Exactly. When I'm halfway up, I only have half as much cable. So I got to figure out a way to do this. So what we're going to do is, how far do I have to move any? We're going to take up that piece of cable right there. Let's say that's the ith piece. It's going to sound like a Riemann sum because it is. And I got to pull this piece here. Let's say I've got to pull it 1,000 minus y feet. Okay. If the bottom is 0, then the cable at the top, let's say you're 999 feet off the ground, then you only got to pull that thing 1 foot. Everybody agrees with that, I hope. When you're all the way at the bottom, the 1,000 feet, whatever that is, you got to pull that 1,000 minus 0. When you're 100 feet off the ground, you got to pull 1,000 minus 100. So you got to pull it 1,000 minus y. Let's say that's delta yi thick. Delta y would be a distance, okay? Delta yi feet. So therefore, the weight of this piece, let's call it the ith force. I'll use, because we call that weight. The ith force, the amount of force required to pull that piece right there is how much that piece weighs, which would be this times the distance I have to travel. Okay, this would be 2 pounds per feet times this many feet, that's now pounds, times this distance, that's now pounds times feet. And I'm sorry, I said force. I'm sorry, work. Sorry about that. The units, this is pounds per feet times feet times feet. That's how much work is required to do this one. So if you guys remember from Calc 1, when I now do the summation, and then I take the limit of the summation, we can generally go directly to the integral at this point. Once we figure out the arbitrary slice, we can go right to that. Now, how far? Well, I'm going from 0 to 1,000. Now, this calculation is trivial. Is this how much work is required to lift the weight?
We need to add the weight, the force for the weight itself,
So what are we calculating here? What is this? The work for the
cable.
cable. So everybody understand there's two different calculations in this problem. So maybe I should do this. Work for the cable. Okay, let's call this a rock. It's a big old rock. And then I have the work for the rock. Do I have to integrate the work for the rock? This is not a
No.
trick question.
It's a constant.
Because the weight is never changing, it's a constant force, the calculation is trivial. The cable is not a constant force because the more I pull on it, the less cable, the less the remaining cable weighs. So that's why the cable would be considered a variable force. Because again, less cable, less work I have to do, but this is never changing. So this is simply going to be the product of its weight times the distance I pulled them. And my final answer will be the sum of these two. Now, I'm going to leave this and move on. If you look on Canvas, if you haven't already, under the notes, I've got some pre-written notes on this stuff. And I do a problem from beginning to end with a little bit of detail. And I explain all the little pieces in case any part of this, went by you. So that should hopefully be very, very helpful. One of the things that I do is I do a lot of posted lecture notes, not everything, but sometimes you need a little more detail. Somebody have a question?
If y is the distance pulled, wouldn't work for the rock be 500 times y instead of 1,000 because you're not necessarily pulling it all the way up?
But I think
I'm
we
sorry,
are.
I-
pulling it all the way up.
There's 1,000 feet that I need to pull. Right?
Yes.
Yeah, he stated he's going to push it all the way up.
You were taking.
Okay.
Okay, but let's change the question. Let's say all of this is 1,000, everything's the same, but I only want to pull it up 300 feet. I want to pull it 500 feet. Well, then that makes it easy.
Just change the 1,000 to
And
the
change
distance.
1,000 to how far you pull it up. Does that help?
Yes, but then you'd also have to change the work for the rock. So wouldn't it
So,
be
how far you pulled it? This rock,
Yes.
I pulled 1,000 feet. I
Okay.
pulled this all the way up. So
Mhm.
put it another way, the distance I pulled the rock should also be the upper limit on the integration, because that's
Yes.
where I'm. So in every textbook, there will be work problems of this nature where it'll say everything's the same, but you're only going to pull it maybe halfway up or pull it, 300 feet. Instead of the full 1,000, you're going to pull a little bit less than the 1,000. And that just means it's going to change your upper limit. That's it. That's a simple fix. And that one is kind of nice, Now, next thing we're going to do, the last thing we're going to do today, is another problem from an integration standpoint that's relatively simple, but from a physics standpoint is really, really huge. In fact, it's one of the very few applications that we do again in Calc 3. In Calc 1, you did optimization problems. Remember, maximizing and minimizing, subject to constraints. And not everybody loves those, but those are generally considered the most important applications. You do that one in Calc 3. We're going to do what are called center of mass, which you will also do in Calc 3, but I'm only going to give you an exposure because we're doing two-dimensional calculus. We live in a 3D world. So next semester, we're going to take what we did in this semester and expand on it, because really the big problem really is a three-dimensional problem. Right? You don't have a lot of centers of mass in the real world of two-dimensional shapes, but we have to start somewhere. So the concept of center of mass, the simplest way I like to think about this is, okay, you got the huge, that was supposed to be the handle, sorry. You got the huge kid, and you got the little guy over here, and you're sitting on the teeter-totter, okay? I have a lot of kids that did a lot of teeter-totter work. Well, tell me about this teeter-totter. It's going to be like this, right? It's going to be just way down here, and there's not going to be a whole lot of movement. Now, this is called a fulcrum. Right now, it's in the center. So let's just say, hypothetically, that this kid weighs exactly twice as much as this kid. Well, obviously, it's never going to balance. So short of having the big kid lose a lot of weight, how can I get this to balance? Like move the fulcrum. But where should I move the fulcrum? This is actually one of the most basic fundamental physics laws. Some of you maybe even learned this in elementary school, believe it or not. You didn't do it from this context, maybe. If he weighs twice as much as him, or she weighs twice as much as her, or vice versa, this person weighs twice as much as this person.
Well, if they were equal, you put it in the center. So maybe we could use that as a reference.
Okay, but they're not equal. So therefore, well, it turns out, now think of the distance. There's something called the moment. And we use capital M, which is probably a terrible choice because moment, you only use moment with mass. They're never used apart from each other. And we use an M for both. So we use a little m for mass and a big M for moment, which is, yeah, really, really helpful sometimes. Moment is basically, think of it as weight. It's force, but it's weight. Weight times displacement. Things can only balance when the moments are equal. So where should I put the fulcrum? Should I move the fulcrum to the left or to the right?
To the right.
To the right, so that this distance is exactly twice this distance. Then they will balance. Some of you may have heard this before. Maybe you've done this yourself. Maybe you got a car and it's stuck in the mud, or you've got a large object you need to lift. So you put a rock, you've got a big object. So you have a rock maybe right here. Here's a rock. And you have maybe a metal rod or something really strong called a lever. And you put the lever under here and you pull down and you lift the rock. You say, how is that possible? Using this. If your lever isn't going to break and you move the rock close enough to the big heavy object, then when you multiply that by that distance, as long as your force times this distance is equal, you can elevate the thing. That's as old as time itself. I've actually lifted a car out of the mud doing this. I had to have a pretty long rod, but it's possible. So the idea is when the moments are equal, you have balance. That's it. So using that idea, now I want you to imagine you have a bunch of individual masses. And by the way, in this case, when we say center of mass, we say center of gravity, center of balance, barycenter. These are all exactly the same thing. Centroid, they're all the same thing. And it really doesn't matter if you're using weight or you're using mass. See, if I said we're using the mass of those kids or we're using the weight of those kids, well, technically the moment is the mass times the distance. But if I used weight times the distance, it still had to be equal in order to balance. That's the key thing here. So imagine you have on a line, you have several different mass points. You have different masses at different places. And what I want to do is put the fulcrum exactly where it's going to balance. So let's just say that's mass 1, that's mass 2, and so on, dot, 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 and that's eventually mass n. I have n mass points. Now, when I say, well, how far away? Well, I need a measuring place. I need a place I'm going to call 0. And what I do in the classroom situation is I usually take one row, or technically column of people, and say each person's sitting at a desk, and now there's space between them and the next desk. So think of this is a person at a desk, this is a person at a desk, this is a person. And what I'd like to do is, if they're all sitting on the same balance beam, if you will, I want to put the fulcrum exactly where I can balance them. But there's no mass between them. They're individual mass points is what we call them. And so how do I find that balance? Well, I need a 0. I need a place that I'm going to call 0. So let's call this the x-axis. Let's call this the y-axis. Then I can call that x1, x2, and so on all the way up to xn. So mass 1 is at x1, mass 2 is at x2. And where you're calling 0 is rather arbitrary, but you need a place you can start measuring. I can just say, call the wall 0 and then measure from the wall. Now, we know there's got to be a place where it balances. Let's say that place is right here. And let's call that x coordinate x bar. That's kind of the universal name we're going to give it. At whatever distance x bar is from the wall, so x bar would be some positive number, that's where the balance must occur. Now, I need to calculate x bar. I can't possibly know that ahead of time because there's an infinite number of variations of the x's and the m's. So given a certain, n mass points at just random distances. Assume all the masses are different, by the way. It makes it more interesting. Assume all the x's are not equally spaced. They're just random. To find this means that the moment to the left and the moment to the right must be equal. But how do I know what that is? Well, if given that there is an x bar, let's just calculate the whole moment. Well, first of all, what's the total mass? The total mass would be m1 plus m2 plus mn, which we could also write the sum. I know a lot of you don't like sum, but I can write it like, oops, the sum from I equal 1 to n of the individual masses, okay? Now the moment, now here's one of the quirky notations we use. This is the y-axis. So the moment to the y-axis, we use a capital M with a subscript of y. But you say there's only x coordinates. You're right, there are no y coordinates. But what is my x value? It's the distance from the y-axis. So that's why it's called the moment y. It's the moment to the y-axis, okay? Because later on, there's actually going to be a moment to the x-axis when we get in 2 dimensions. So this has got to be the sum of all the masses times distances, but not m1, x1, m2, x2. No, the distances. Oh, so the distance to the fulcrum, remember? So that would be x bar minus x1. So this would be m1 times x bar minus x1 plus m2 times x bar minus x2 plus all the way to plus mn x bar minus xn. Now, once I get past, aren't all the x bar minus x is going to be negative at some point? Now think about this logically. Everything to the left of here, x bar minus the x coordinate is obviously a positive number. And everything to the right of x bar, that's got to be a negative number, because I'm going this minus that coordinate. But if the moment to the left has to equal the moment to the right, and I don't know where this is, but I simply always say x bar minus the x coordinate, then half of this is going to be positive and half of this is going to be negative, and this sum will have to add up to what? 0.
The 0.
If that is truly the center, this has to add up to 0, because half of it will be positive, half of it will be negative. I just don't know where x bar is, but this will allow me to find it now. This is a very simple process. So if I go ahead and distribute, okay, if I go ahead and distribute this, I'm going to see m1 x bar minus m1 x1 plus m2 x bar minus m2 x2 plus all the way to the end mn x bar minus mn xn. And since that equals 0, why don't I throw all the minuses on the other side? Then I have m1 plus m2 plus all the way up to mn, times x bar. And on the other side, I have m1 x1 plus m2 x2 plus all the way to mn xn. But if you look at the left side, isn't that the total mass? That's the total mass.
Professor,
Yes.
could you re-explain just the part where you took the x bar out with like m1 plus the last full row that you wrote?
Oh, okay. I said take all the minuses and throw those on the other side of the equals.
Understand. Got it.
So what do I have on the left side? Everything's times.
Right.
I'm just factoring
Thank
out
you.
the x bar. Does that make sense?
Appreciate it. Yes.
So now what do we have on the right side? Well, isn't this by definition the total moment? Those are all my m's times x's. So this is the total moment. I'll call it that. I think we've just figured out what x bar is. X bar equals, I'm going to write in simple words, the moment of the mass. It's actually that simple in real life. I want to find the center of mass. This works for the teeter-totter example. I take the total moment, I take the total mass, and that's from the 0. Cool, because x bar is our point. That is my center of gravity. That's my center of mass. Now, I overly simplified it. I overly simplified it because I said I have a bunch of individual mass points. What if I have variable mass? I have a tree branch. Let's say it's relatively straight. I have a tree branch. Is the center of gravity of the tree branch exactly the midpoint? Not necessarily. I might have, knots in one area. It might be thicker in one area, thinner in another. I might have woodpecker holes in another. I think it'd be more reasonable to assume that this tree branch is constantly changing. In other words, it has what's called variable density. Oh, so I can't simply multiply. I might have to integrate. So if I have variable density, we're almost there. And again, I've got an actual whole nother video on this stuff. We use the Greek letter delta. Remember epsilon delta? The Greek letter delta we generally use for density because D, density. So if I have variable density, now the problem with the word density is it's absolutely ambiguous. There's exactly 6 forms of density, and I don't mean English standard versus metric. There are 6 forms of density. Density can be mass or weight in the numerator. It can be mass per length, mass per area, mass per volume, and then the same things with weight. That's 6 different versions of density. So density is always specific to the problem you're looking at. So we're using mass right now. And if I said, I have a thin rod, I have a tree branch, I'm not thinking this way, I'm only thinking this way. So I'm thinking of this as one-dimensional. So now my density would be mass per unit length. But if I'm looking now at my tabletop, and let's say my tabletop is all different, it's wood, but maybe, again, woodpeckers and knots and things like that. My tabletop has different density at every point. So now it'd be mass per unit area. Okay, now I have, I brought in a block of wood from outside. I'm going to burn a, piece of wood. Now that's 3 dimensionals. Now it'd be mass per unit volume would be my density. So density is not an automatic thing. You always have to define what your density is. So if I have a one-dimensional thing, okay, and I have variable density, then my mass, this would be mass per unit length. Then my mass would be the integral of density dx. Let's say that's A and that's B. So just from beginning to end. That's a fairly trivial thing. That's not a difficult thing. If I said, what's my moment? Now, remember, moment is the distance times the mass. So I would then say the moment, again, to the y-axis, because we're measuring in that direction, everything's exactly the same, except now I have an x, because that's the x that I'm multiplying by the mass. That's it. If I have variable density, now the only thing we do in a class like this is we make sure that the densities are usually really, really simple. Like my density is 3x, something really, really trivial. So we don't get stuck on the integration. This is all about the setup, not about the answer so much, because the answer we want to be easy. So now what's the big problem we want to look at? What if I have a 2-dimensional thing going on here? All right, I have a tabletop. I have a desk in front of me and it's got strips of wood. All right, so let's say, keep it simple. I'm bounded. So here's my region in the XY plane. And I have variable density. I would like to find the center of mass. Another way of thinking about it, this is a 2-dimensional thing. Where would I put my finger if I laid it flat? Where would I put my finger to balance? Now, every 2-dimensional object has a center of balance. That's an absolute, it's not even a complicated thing. We could spend a week just doing the geometry of stuff like this and symmetry. It's really, really cool. But the idea is, if I have my textbook here. This is a 2-dimensional book, but I could put my finger somewhere. The thickness of the book is not relevant. It's the area of the book. I just grabbed a book here. So I want to put my finger exactly where this balances. But if the density of this thing is variable, then my finger is not going to be in that geometric center. It's going to be off center somewhere. If my density is constant, which it could be, then it's really, really easy to locate that center of balance. But the problem is, in real life, densities are rarely constant. I mean, the human body, you're made of bones and flesh and blood and everything. No, you're definitely not constant. Heck, even the car, right? The car is not constant. You have metal, you have plastic, you got other things. So the first thing we're going to do is our density is going to be a function of X only, which means our density is only going to change left and right. It will not change as I move up and down. And that's really important. Calc 2, our biggest limitation is we can only do problems with one independent variable. Next semester in Calc 3, we do the two independent variable problems, because that is actually the way of the world. But for now, we're limited. So what we're going to do, imagine we're going to split this up into a bunch of pieces, the whole Riemann sum thing, right? I'm going to square one off and say, I want to figure out how to find the center of mass of any of these. Well, first of all, how do I find the mass of this shape? Well, the mass of this shape is fairly simple. If I know that the area, the ith area, okay, think Calc 1, the ith area would be, let's say that's the ith rectangle. That would be f of xi minus g of xi times delta xi. That's the ith area. So therefore, what is the ith mass? Every one of these strips is going to have a different mass from left to right. So I'll call it little m. Well, that should be the ith area times the density. Okay? Because that's what it is. This density is now mass per unit area. In the previous problem, it was mass per unit length. This is an area problem. So if I want the integral for mass, we'll use little m. I know what that integral looks like. This integral is just going to be f of x minus g of x dx from a to b. If I took out the density, that gives me the area. If I throw the density in there, now I have the mass. Density cannot be factored out because that's a variable. That's not a constant. And I've actually seen people come up with formulas that are not correct. And I was like, where did you get that? Oh, I went to the internet and this is what it showed me. Oh my God, no, don't go to the internet for this. This is too easy. Yeah, this is the formula. There's not a different version of this. This is just this. We have only the x. Now, the tricky part is, how do I find this moment and this moment? See, I now have two moments. I have a moment to the x-axis and a moment to the y-axis. We already knew how to find the moment to the y-axis. That didn't change. Remember, it's this with an additional x in there. That's what we did before. So I'll call it capital M to the y-axis. That's easy. If I just go to this, in fact, I'll write it right here. Capital MYI is going to be AI density and then times the x. That's it, because I'm multiplying mass times an additional x, that being capital. So this integral is really easy to state. It's probably going to be easy to do because your f's and your g's, the one thing we tend to do in Calc 2, we limit the f's and the g's to things like lines and parabolas. Really, really simple regions that you can easily integrate. Great, that's my moment. Now here's the hard one. I'll put down here. My moment, capital, make that more capital. My moment to the x-axis is going to be a little bit trickier. Okay, and here's why. If this is the moment to the y-axis, involves that's the x distance, then the moment to the x-axis must obviously involve the y distance. That's kind of a no-brainer. I'm involving this distance, except this produces just a teeny little problem when I want to integrate. Anybody want to tell me what the teeny little problem is that I'm going to run into when I want to integrate this?
You have you have x and y.
I have two variables, which, by the way, if you only have one independent variable, that's an absolute mathematical impossibility. Anything I wrote is just garbage. You cannot have two variables, and there's only one independent variable. You can only have one. So our dilemma is, what do I do with the y? And here's the trick. And this is the part that might feel confusing, but actually simplifies things tremendously. Remember how I said the density does not change when you move vertically? Since the density does not change vertically, if we go back to the problem where I was pulling up the weight with the cable, do you remember that? If you go back to that problem and you said, let's take the whole length of the cable and let's make all of the mass, literally of the cable, just imagine all of the mass was at the dead center of the cable. Now that's not realistic from a practical physical standpoint. But if I said, imagine all of the mass was at the center and I just have to move that thing, whatever half the distance was, you're going to get the same answer. It's kind of cheating, but it would work, but only if you're doing it the whole length. So what if I said, this thing has a certain amount of mass, but since it doesn't change going up and down, what if I pictured all of this as if all of the mass was in the dead center? It turns out that will give me the calculation. How do you find the dead center of these? That would be the average. So I'm going to replace the yi with the average. So I'm going to replace this with 1/2 f plus g. That's how you find the average of two things. You take half their sum. That means that this formula would then become, okay, not x anymore. I want this, which I can write as this. And then the rest of it was f. I'm sorry, there's no I here. Sorry about that. Now, again, understand that the nature of the problem is probably going to be pretty simple functions. When I ask these questions, I think the most complicated function I ever use is maybe a parabola, like y equal x squared, just so you don't get lost. Now, a lot of folks look at this and say, well, why don't I multiply these out first? And I say, why would you do that? No, you're taking something simple and making it complicated. No, order of operations say simplify this, and then multiply them. I guarantee you that'll always be easier. You see, these are probably going to combine. These are probably going to combine. If f is let's say a parabola, it's written as a trinomial, and g is a parabola written as a trinomial, and you really want to multiply these out, trinomial times trinomial minus trinomial, that'll take you an extra half hour to do these. No, simplify that, then multiply that. 100% of the time, do it like that, because a lot of times what you're going to find is this lower one might actually be the x-axis. And if the lower one's the x-axis, that means that the g function would actually be 0. Ooh, then you're really happy. You like that one. This problem is or isn't difficult based on the complication of f and g, not based on the setup. The setup is fairly simple. Now that I've got this, though, my goal was to find that center of mass. But in this problem, that center of mass is a coordinate. It's an xy. It's not a value. So how do I find it? Well, how did we find x bar before? We said it was the y moment over the mass. I'm going to try to make those. That's big M and little m. Therefore, the y bar should be the x moment in the mass. Remember, that's the distance to the x-axis involved, which is a y value. That involves distance to the y-axis, which is an x value. That's how you remember these. And therefore, what is the answer to the question? That's my answer. These, generally speaking, in this class will be simple to calculate. They're going to probably be fractions. They won't be irrational generally, just because of the nature of the problems that we're going to use. Now, I'm pretty sure I did everything right. And I get an answer. Are there some things that must be true about my answer? You have a region, I'm going to be really generic. And here's your x bar, y bar that you just calculated. Does anybody have a problem with that? Please say you have a problem with that.
I have a problem with it, but I don't know why.
Well, I have a thing. Remember, I need to put my finger. I'll use my cell phone. That's lighter. All right. So there's a spot on my cell phone that will serve as the balance point. You all agree with that? But what if I said the spot on my cell phone's out here? So when I put my finger out here, I don't think that's going to balance. You?
Yeah.
So tell me what's the problem with this answer?
Way off from it's not even in your shape.
It probably should be within the closed region. And that's like the ultimate, oh, geez. I just did a problem where my entire region's in the first quadrant and my center of mass is in the fourth quadrant or the second quadrant. It's not even in the shape. That would be a problem. I'm just saying that I don't want to say it's a simple error check.
Mhm.
Now, can mass ever be negative? It's not a trick question. Can mass
No.
be negative? No. Can a moment be negative?
Yes.
Yes. If my region is in the second, third, or fourth quadrant, doesn't at least one of the values have to be a negative number? In fact, let's say my entire region was in the third quadrant, then wouldn't both of these be negative? So go back to here. If mass is strictly positive, a moment can be negative. That would just mean you're not in the first quadrant. That would mean your X bar or Y bar was in a different quadrant. That's okay. Moment can be negative. This is why when you're doing this problem and you're practicing, please draw the picture. Oh my goodness, that's the easiest thing, but draw the picture. Because if you do your calculation and you're looking at your picture going, my that is like, 3 units out and 4 units up, and I've got a point in the hundreds. That's probably not a good thing. But what if my answer was like right here? You go, I don't know. I think I'm, depending how extreme, you can't take your picture and your answer and say it's absolutely correct or it's not correct, but you can identify ones that are absurd. This would be absurd. If my answer was here, I don't know if that's absurd. I think it's probably reasonable because I have variable density. Remember, I'm not going to get the perfect center in all likelihood because my density is probably increasing as I move left to right. That's probably the way most of the problems will look. So most of the problems will probably be, shifted a little bit, and that's okay. But you want that answer to make some sense at the end because the calculation won't be difficult. Now, the last part about does it have to be within the shape? That's a trick question. Because we're doing y as a function of x in these pictures, we're never going to get something utterly absurd. But let me give you something utterly absurd. I'm bounded by multiple regions. Let's say I'm bounded by, I'll keep it simple. I'm bounded by this, and I'm bounded by this. Okay. I want to find the center of mass of this shape. Now, remember the shape itself, it's two-dimensional. It's a cardboard cutout. I want to find the center mass, regardless of what the density looks like. Do you suppose it's reasonable that my center of mass might be somewhere in here?
Yeah.
Yes.
So is it possible that a center of mass is not actually located physically within the enclosed region? Yeah.
Yes.
I had to kind of go out on a limb here. Right? Do you all agree that you say, yeah, I can see that being probably somewhere in here. That's okay. But this is not made up of multiple things. This is just two curves from here to here. So this one, yeah, probably should be in. When I first begin this and I'm in a classroom, I usually I'll bring some props. One of the things I love doing is something like, think of a horseshoe. Now, okay, that's a terrible horseshoe, but you got the idea. Now, I'm going to lay the horseshoe flat and keep it simple. I'm going to put it on a stiff piece of cardboard. And now I'm going to put my finger under to balance it. Wouldn't it be reasonable? The center of balance is probably somewhere here when I lay it flat. Does that seem reasonable to everyone? Yeah.
Makes sense.
But this is not bound by functions. Think about that. Those aren't functions. There's no way I can do functions that would make a horseshoe. So like this problem in here, and my favorite example of all is a hula hoop. I have a hula hoop. There's nothing in between here. Isn't the center of balance of the hula hoop the dead center of the circle? Yeah, and it's not part of the hula hoop. There's nothing in the middle of the hula hoop. The hula hoop is a solid ring. So in certain scenarios, now, if I give you a circle of constant density, you know that the center of mass is the center of the circle. That's not even a question. So if I gave you a circle of variable density, you're expecting it to be shifted. I just want you to get the conceptual part. We aren't doing anything meaningful in this area. I'm sorry to tell you, because it's two-dimensional with one independent variable. Next semester, we do the calculations for three-dimensional objects with variable density, because now it's I have a piece of furniture and I want to know where the balance point is. We talk about constructing a building. What about the center of gravity? What about a car, the center of gravity? We're talking about three-dimensional shapes. And it turns out, if you're an engineer, this is one of the more important applications you need to understand, because you don't want things to tip over, that kind of thing. So we're only getting our feet wet. So the level of calculus required to answer these questions is very low level. The most you're going to do is integrate a simple polynomial. I promise you that. If it turns out the problem you're doing is way beyond a simple polynomial, then there's probably an error in the setup. So always go back to the setup. And I am less concerned with the answer to the question as you presenting me the correct integral. Now let's go back to Calc 1 for a moment. When you found the area between two curves, or you had a region and then you rotated it about an axis and you found the area using either the disk method or the shell method, you did stuff like that. The integrations usually weren't that complicated. And in fact, it was the statement of the integral that was the most important. So I'm notorious on my calculus exams. You have an exam where you're doing integrations all over the place. You're doing integrations with substitutions, changing the limits, all the gnarly stuff. And now I'll give you a volume by rotation problem and I'll say, state the integral. Or I'm going to give you a surface area or an arc length and I'll say, state the integral. And you'll say, wait, you don't want me to integrate it? No, I just want you to state it. Because you've already proved to me in another area that you know how to integrate. I just want you to state the integral, because if you can state the integral, I'll give you the benefit of the doubt that you could have integrated it. In my Calc 3 on these problems, I usually just say state the integral for the mass and the moments, because they're already pretty good at integrating, and the state, if they state it correctly, I'm pretty sure they could finish it. And that's kind of the idea. These problems I want you to finish because they're short and sweet. But on an exam question, I will sometimes just say, calculate the mass, or calculate the mass and state the integrals for the moments, just demonstrating that you understood what was going on. And that's a time thing. On a take-home quiz, now you can do all of it because you have all the time in the world. Now, last thing I want to mention today, and it's about the quizzes. Now, there's always some confusion on, like, how do I turn in a quiz on the internet? Well, that's actually the easiest thing. You take a picture with your cell phone. But it's the getting it to me that's always the tricky part, because a lot of folks will take pictures and I can't open it, I can't see it, it's poor quality. There's a really simple app that most of the people at Mesa have been using since the beginning. It's called Fat Scanner. If you don't have this already, there's a YouTube tutorial that takes like 1 minute and 40 seconds. It's like the easiest thing in the world. You put it on your phone, it download, it's free. But the Fast Scanner app, when you simply take the pictures. If it's an exam, it's picture, 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 send. From beginning end, it can't take more than 1 minute. It's so simple and so idiot-proof to use. And the thing about the Fast Scanner app is you can control the contrast. So if it's coming out really light, you can darken the contrast before you resend it. So it's the easiest thing. Now, having said that, I have a lot of people that, well, I'm going to do it my way. And then your way, I never actually receive, like ever. Do not take a picture, send it to your own computer, download it to your own computer, and then send it to me from there. More often than not, that one fails hopelessly. No, take a picture, send it to me, email it to me from your phone. It is really, really, really simple. Okay. Now there's a bazillion versions of something like this. If I don't get it on your very first try, then ditch whatever you're using. And I will say at least 1/3 of the students have difficulty on every single thing they send because they say, I'm going to do it my way. And their way doesn't work. And I don't know why. And every single class, when we get to exams, there's at least one person in every class that will keep me after for 30 minutes to an hour because they can't figure out how to send me their exam. And everybody else is picture, 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 send. No, it should be picture, send, because it sends it to me as a picture. I don't want it sent as a file. Send it as a picture. To convert it to a file now involves memory and other things, and your computer may reformat, or your computer might reformat it. Nope, the easiest thing in the world. And if you're not sure at first, you can always ask, hey, did you get it? Now, here's the next thing. Some of you will have sent me it, and you thought you did everything right, but it didn't send. It's stuck in cyberspace somewhere, and it's just, or spinning around in your phone, you didn't even notice it. What usually will happen is when I will post the grades really, really quickly, and you'll see a 0 for yours. It is extremely rare that somebody does a quiz and gets a 0. I mean, you've got to really, I give you points for spelling your name correctly, even if I don't know how to spell your name. It's really hard to get a 0 on anything you're turning in with me. So when you see a 0, it means I didn't receive your quiz. It's that simple. But you sent it, I didn't receive it. Here's the best part about doing this with your cell phone. When you took the picture and you tried to send it and it didn't send, the original date and time you attempted to send it will still be attached. So when you get the 0, because I never got it, you can just email me and say, hey, did you get my quiz? I saw a 0, and I'll say, no, resend the original email. And when you resend it to me, it will have the date and time you originally sent it. That's your insurance. Of course, I'll accept it because you did send it on time. I just never received it. Does this happen often? This happens at least once on every quiz, on every class, in every class, every semester, at least one person, and it's never the same person. It's like the internet chooses you at random, right? The universe is going to get back to you in some way. Almost everybody here will have one time when I didn't get their quiz, and it's unforeseeable. So just simply resend it. Now, if you never sent it, you can't say I sent it, you never got it. Because then when I ask you to resend the original, you won't have an original to resend. So that won't work. When you resend it, it will always have the date and time of the original transmission. And that's, again, that's a wonderful way to go. So I'm going to stop now.